All right, let's jump right in. We're about to unpack a concept in pharmacology that, on the surface, sounds completely and utterly impossible. It's a real head-scratcher, a paradox that revolves around a number so huge it just doesn't seem to make any sense.
15,000 liters. Just think about that for a second. To give you some perspective, your entire body, all of it, contains about 42 liters of water. So how on earth could a drug be taking up a space that's hundreds of times larger than you are?
That's the question, right? How is that even possible? Does the drug magically expand? Do we have some kind of hidden extra-dimensional space inside us? Well, the real answer is actually a lot more elegant, and it tells us something really fascinating about how medicines actually journey through our bodies.
So here's the official definition. Now there's one word on this slide that is the absolute key to unlocking this whole mystery, and that word is theoretical. That's the secret right there. The volume of distribution, or VD, it's not a real physical space. It's a calculated value, an apparent volume. Think of it as a measure of how a drug behaves, not where it physically is. Now to really wrap our heads around this, let's forget the complicated biology for a minute and use a simple analogy, a tank of water and some sponges. Okay, so just picture your bloodstream as this big tank of water. Simple enough. Now, we're going to add our drug, which we'll imagine is just one single drop of a really strong blue dye.
But here's the twist. Your body isn't just an empty tank. It's a tank that's filled with sponges. Your fat tissue, your muscles, your organs, they all act like sponges. And certain drugs, like our blue dye, are super attracted to these sponges and just get soaked right up.
So, what happens when you try to measure the concentration of the dye left in the water, that is, in the blood? Well, it's going to look incredibly low, right? Because almost all of it is hiding out in the sponges. Now, if you didn't know the sponges were there and you just saw how pale the water was, you'd think, wow, to get a concentration this low, that one drop of dye must have been diluted in an absolutely gigantic tank. And that gigantic, imaginary tank, that's the volume of distribution.
And this really gets to the heart of it. The VD isn't some anatomical measurement. It's just a number that reflects a drug's personality, you could say. It tells us how much a drug likes to leave the blood and go hang out in the body's other tissues, our sponges.
Okay, so if it's just a reflection of behavior, how do we end up with a hard number like 15,000 liters? Well, you might be surprised at how simple the math actually is.
It's really just a simple division problem. You take the total amount of the drug you put in, and you divide it by the concentration you measure in the blood. So think back to our sponges. If that concentration in the blood is a teeny tiny number because the drug is hiding in the sponges, well, a tiny number on the bottom of that equation is going to give you an absolutely enormous result for the VD.
Which, of course, leads to the next big question. What makes one drug act like a sponge magnet while another is perfectly happy just staying in the bloodstream? What makes a drug spongy?
It really boils down to three main characteristics. First, is the drug fat-loving, or what we call lipophilic? If it is, it's naturally going to want to leave the watery blood and store itself in the body's fat tissues. Second, how tightly does it bind to proteins that are already in the blood? If it doesn't hold on very tightly, it's free to wander off into the tissues. And third, does it have a strong electrical charge? Drugs with little to no charge can slip through cell walls much easier.
Okay, the theory is one thing, but let's make this really concrete. Let's check out a few actual drugs and see how these properties lead to some wildly different volumes of distribution.
Take a look at this. On one end of the spectrum, you've got warfarin. It binds super tightly to proteins in the blood, so it basically stays locked in the bloodstream. Its VD is only about 8 liters, barely more than your blood volume. But then, look all the way at the other end, chloroquine. It is extremely lipophilic. It absolutely loves hiding out in fat tissue. And its VD, there it is, our staggering 15,000 liters. So here's the bottom line. Warfarin is like a dye that pretty much ignores the sponges. It just stays in the water. Chloroquine, on the other hand, is a dye that gets almost completely soaked up by the sponges, leaving very little behind in the water for us to measure.
And this chart just says it all, doesn't it? I mean, look at that scale. Warfarin is just a tiny little bump on the left, while chloroquine is a skyscraper. This shows it perfectly. It was never about a physical space. It was always about the drug's profound preference for tissues over blood. The mystery of the 15,000 liters, it's solved.
Okay, it's a fascinating concept, for sure. But is this just a weird piece of medical trivia, or does this strange theoretical number actually have a real-world practical use for doctors and their patients?
Oh, you better believe it does. Yeah, this isn't just some abstract idea. This one number is absolutely critical for calculating something called a loading dose. And that first dose can sometimes be a literal lifesaver.
See, if you have a really serious infection, you need that antibiotic to start working right now. But if you give a normal dose of a drug that has a high VD, almost all of it is just going to vanish into those tissue sponges, and it won't do anything in the blood where it's actually needed. By knowing the VD, a doctor can calculate a much larger first dose, a loading dose, that's big enough to fill up all those sponges and still have enough left over to reach a therapeutic level in the blood right from the get-go.
So in the end, that crazy paradoxical number isn't really about the space a drug takes up. It's a single number that tells a whole complex story, the story of a drug's journey, its preferences, and its ultimate destination inside your body. It really answers the question, when you take your medicine, where is it really going?